All right, everybody, let's take a look now at the speed is equal to r omega, but let's get into the vector aspect of this. So I want to know what's the vector velocity based on the r and the omega. So let's take, just for the sake of argument, let's take this outside point B, and we've got some vector radius out here, and that radius is in the I hat direction. I'm going to keep that in the I hat direction just to make life simple. So the radius is in the I hat direction. I could move it to any place, it doesn't matter, but this just gives us a better idea of what's going on, right? And then I know that as this rotates, this point is rotating up. And so the velocity vector while it's over here must be in the j hat direction. So there's a j hat over here. And I'm trying to get this relationship so that it works out the way I want it to. Omega, this is rotating in the counterclockwise direction. Omega is pointing in the k hat direction, right? So I have an omega times k hat here. So I need to multiply these. Now I can't use a dot product. That's not going to work because if I do a dot product, well, first off, I'm going to get 0. But secondly, when I do a dot product, I get a scalar quantity. That's not going to work. I need a vector quantity. So I need a cross product. I need a cross product. So the question is this going to work? That's the question. So let's think about the unit circle for cross products, right? We go in the counterclockwise direction. I cross j is k, j cross k is I, k cross I is j, j cross I is negative k, because I'm going in the wrong direction. I don't know if you've seen this before. But the point here is I get I cross k is in the wrong direction. So that's a negative j, but I don't want a negative j because it's definitely going that way. So these must be needed to be reversed. So it's got to be k cross I because k cross I points in the j direction. All right, and so the actual relationship then is velocity equals omega crossed r. And that's how I remember that. I always think about that unit circle and then this point on the far right-hand side. Again, it doesn't matter if I'm over here or someplace else. This relationship is always true. I've just kind of shown you what the relationship is based on a nice place on the unit circle. I made my life nice, right? And so there's my relationship, but it's always true. Always, always, always. So the vector velocity, the vector quantity, is going to be omega, which usually points in the k hat direction, crossed with r. Okay, it doesn't have to though. It doesn't have to point in the k hat direction. In fact, in reality, if I consider out of the board k hat, this is at another angle, but it doesn't matter. Okay, so let's stick with that. Now, what about the acceleration? Well, the acceleration, we already know the acceleration is the derivative of velocity with respect to time. Right? We've known that for like quite some time. So let's do that. Let's take the derivative then with respect to time of omega crossed with r. Well, this is a cross product, and so I need to use the product rule in order to solve this out. And so let's do that. So the acceleration equals the derivative of omega with respect to time crossed with r plus omega crossed with the derivative of r with respect to time. Right? Derivative of the first times the second plus the first times the derivative of the second. That's the product rule. But d omega dt, we learned that in a previous video, that's alpha, which is also a vector quantity. That's the angular acceleration. That's the angular acceleration. That's alpha. Go back to some videos that we had on the radial transverse, and you'll see the same thing happening here. Over here, what do I have? I have omega cross dr dt. That's omega crossed with v. But v is omega cross r. So this comes out to be alpha crossed r plus omega crossed omega cross r. You got to be really careful with the parentheses. If I do omega cross omega, they're parallel to each other and I'll get 0. Two vectors of the same direction or anti-direction will give you a cross product of 0. So I can't do that. I have to do omega cross r. Well, let's figure out what direction that's in. Alpha cross r, let's do that first. Alpha cross r, alpha will be out of the disk, and then r is in that direction. So alpha cross r is in the j hat direction, or minus, depends on if it's speeding up or slowing down, right? If I'm speeding up, then alpha is in the positive k direction, but if it's slowing down after I let go, it's slowing down, then alpha's in the negative, and that would be then an acceleration which is down in the opposite direction as the velocity. And remember, if the acceleration and the velocity are in the opposite direction, your speed is decreasing, right? Your speed is decreasing. All right, but let's take a look at this. Omega cross r is the velocity. So this is omega cross with the velocity. So it's omega cross with the velocity, which is up. And so my finger points in the direction of the acceleration, which is in the negative x direction. So that acceleration is pointing in this direction, right? That's pointing along the radius, but towards the center. This is the center-seeking acceleration. This is the centripetal acceleration. Go back to the videos again on radial transverse, and you'll pull that out of there. So this is alpha crossed r minus omega squared, no vector, just the magnitude of omega squared times r. So it's in the direction of r, but inward, points towards the origin, right? And that's my acceleration. That's what I'm going to get for the acceleration. So now we have relationships between the omegas and the radii, the velocities and the accelerations. So all of those relationships are now summed up right there. So we're good to go. We've got our angular velocities, angular accelerations, linear velocities, linear accelerations, and our radii all related to each other. All right, we're ready to move on. So if you have any questions on this video, please leave them in the comments below. Thank you very much.